Alright, this is week 12, video 3, I think, or whatever number we're on now. And what we're going to discuss in this video is now that next segment of, okay, well, we have this idea of critical points and extreme values, and we kind of discuss how to find absolute extreme values based on quote-unquote inspection, but now how do we do this algebraically and with multiple variables? And so kind of our single variable parallel said, okay, well, as soon as we find our critical points, we would have to do the first and or second derivative test depending on the situation, and kind of proceed from there. Okay, this is also presuming that we're on an open interval, we're not looking for absolutes. That's a whole different ballgame, which we'll get to in the next video. Anyway, so we're going to focus on kind of this second derivative test idea from single variable and extend that, or see how it extends into the multivariable case. Okay, so we're going to consider or suppose that we have a function, okay, similar definitions to what we had in the last video, continuous second order partial derivatives, okay, that's fine, at and near the critical point. So yes, we do have a critical point, so pay attention to that. Then we get kind of a few different cases, okay? If h of f of a, so again, just remember that h, that's our symbol for the Hessian, okay, so this is the Hessian, or Hessian, I don't know how that's pronounced formally, I'm going to say Hessian. Then we say if the Hessian of the function at the point is positive definite, then we have a local min. That's kind of along our ideas of concavity, right? So it kind of makes sense. If our second derivative is positive, we end up with a local min, would concave up, local min. And then in the case where the Hessian is negative at the point, then we get a local maximum. Okay, so again, that's kind of concave down. And then if the Hessian is indefinite, well, then we have a saddle point. Okay, so then I left little spaces for us to draw little diagrams if we so wish, but the idea here is that in the first case we have a surface, kind of like our paraboloid, that opens up. Okay, and we have a minimum here. Similarly, in the second case, we'd have a paraboloid opening down. Okay, and then for our last case where we have a saddle, let's see, so we have one parabola and something like this, and then we have the other parabola here, and then I forgot to add this. And maybe like right there would be our saddle point. Okay, so it'd be concave up in this one direction, but then concave down in the other direction. Okay, and the other direction being like what I'm showing here in red. Okay, so that's kind of the second derivative test that we're going to be seeing. And then if you just kind of want to think of some justification, maybe not, this isn't necessarily a formal proof, but what we could do is thinking of a critical point, and then what we could really do is think in terms of what we studied last week and look at Taylor polynomials. Okay, and if we do this in the case of single variable calculus, okay, what we know is that at least when we're pretty close, right, we could approximate f of x as being approximately f of a, and then so that's the first, and then or the 0th degree term, and then we have f prime at a times x minus a, and then plus 1/2 f double prime at a x minus a squared plus dot dot dot, right? Okay, and what we know is that this whole second term, isn't this just 0? Okay, because of this little piece here, right? So then, all right, so then we can actually reduce this. We can say this is approximately f of a, and then plus f or 1/2 f double prime at a, x minus a squared plus dot dot dot. Okay, and so on and so forth. Okay, and really what we're going to see long run is that the behavior is going to be dependent on this. Okay, we're going to get some other higher degree terms naturally, okay, but those other higher order terms are going to be dominated by this quadratic term when we get close to a. Okay, similarly for the n-dimensional case where n is bigger than 2, we saw last week that we could say f of x, vector x rather, is approximately f of vector a plus the gradient of f at a, vector a, okay, and then times vector x minus vector a, all right, plus 1/2 vector x minus vector a transpose, then the Hessian of f at vector a, and then x minus a vectors, okay, and then again, because of the way we are finding critical points, this whole term is just 0, and then as a result, what we end up with, this is just it looks very much like a quadratic form, right? So this is a quadratic form on its own. And then we have a shift, okay? So this is kind of the idea behind the second derivative test, okay? In the next video, we'll actually go through an example of using the second derivative test to classify mins and maxes.